Good afternoon, everyone. I welcome you back to my YouTube channel, and of course, this is the mentor Hamper Kliman. So today I bring you yet another tutorial on dimensional analysis, and which happens to be a practice question. A little bit complex, but very simple. Dimensional analysis is very simple. All you have to do is to figure out the dimensions and using them to prove particular quantities in a formula if they are true or not. So in this case, we have a question: write down the dimensions of the following: velocity, acceleration, force, density, pressure. Let me break this down for you. So the dimensions of velocity, so we have velocity. The units for velocity are simply meters per second. The dimensions for meters is simply L. The second is the time, which represents the period. Henceforth, the dimensions of velocity are going to be, where there is m, I put my L. Where there is s, I'll put my period. And those are the dimensions for this particular quantity. We go to B. Acceleration, the dimensions of acceleration. Acceleration is equal to, the units are simply meters per second squared. Using the concept, where there is m, I'll put my L. Where there is s for the second, I'll put my t, which is the period. And this happens to be t to the power 2. Very simple like that. We come to C. They are saying we find the dimensions of force. Well, force is equal to ma, where a is the acceleration due to gravity and m is the mass. Dimensions for mass, okay, is simply big letter M. Then acceleration, we know that it is simply L over t to the power 2. Now, there is a concept which I want to introduce here. Please take note of this particular concept. Take note of this particular concept. I like calling it the MLT concept. MLT concept. Okay, the MLT concept. Very, very good concept and very simple. So using the MLT concept, we can simply say, we can put x here. Then where there is L, I can put y. Where there is t, I can put z. To which x can be equal to some value. Okay, it can be 0, it can be 1, it can be 2, it can be 3. L can also be equal to 0, 1, 2, etc. Z can also be equal to 0, 1, 2, etc. or etc. Whichever value, we call it the MLT concept. Very important concept. So if we are to write this in the MLT concept, this is going to be, because we know that t, this is just the same ones, L over t power 2. So in the ML concept, this is going to be m, then L, then t, where this is going to be negative 2. Basically because we have put everything in in a line like that. Okay, so that is how everything is going to be like. In the MLT concept, using the MLT concept, that is how everything is going to be lined up. Okay, let me just try to clear my board. So, okay, I think I've got space somewhere here. We come to the density. How do we write density in, how do you write the dimensions of density? So this is how it's going to be. The dimensions of density, but we know that density is equal to mass over the volume. We know that the dimensions of mass are simply big letter M. How about volume? We know that volume Please pay attention to this. Volume is going to equal to, how do you find volume? Volume is equal to L times B times H. L is the length measured in meters, okay? Meters. Okay, so in this case, using meters only, we are going to have the volume of meters cubed. Okay, then we know that the meter, the dimensions of the meter, which is equal to the length, is just going to be L3. Okay, L3. So in the MLT concept, okay, let's try it using the MLT concept. In the MLT concept, how can we write density using the MLT concept? We know that here we only have L3 only. L3 only. So meaning where there is M, I'm going to put M to the power 0 for my X. Then where there is L, I'm going to put my 3 just like the way it is. But where there is T, I'm going to put a 0 again. Why? Because I know that M to the power, any number raised to the power 0 is equal to 1. 1 multiplied by everything, it will bring us to L to the power 3. So in the MLT concept, please just write it the same way it is. Don't change anything. I've not changed anything. It is still the same. Okay, this is just the same. This I've written here is just the same as this. Mathematicians know what I'm talking about. All right. We come to the pressure. Let me just try to wrap my board. Okay, so okay, let me wrap the board. All right. We come to pressure. They are saying, we know that pressure is equal to force over area. But we know that area is equal to L multiplied by L, which is just L power 2. This is how we find the area. We all know the units for area. It's a meter squared. So that is just how we find area. Okay, those are the dimensions of area. You should know that. Okay, then we come to the dimensions of force. The dimensions of force, we say that this is just M L T negative 2. Okay, I think we had stated that. Okay, those are the dimensions of force. Okay, I think we highlighted and I showed you the dimensions of force, how they come about, because you know that force is simply ma. This is the m, this is L over T squared. So if you write it in MLT concept, this is going to be M L T like that. Very simple. Okay, so henceforth, where there is force, I can put my MLT negative 2 over. Where there is area, I'll put my L power 2 like that. Okay, so this is going to be cancelled, then this is going to also cancel. Then at the end, we'll remain with M L. Here there is a 1L, so it's going to be negative 1, then T negative 2. These are the dimensions of pressure. In the first video I didn't show you, but in the next video I have showed you. All right, now let's try to prove. They're saying for a fluid with constant density P, the velocity V, pressure P, and height H at points on a streamline are related to Bernoulli's Bernoulli's constant, where g is the acceleration due to gravity. Show that the left-hand side of Bernoulli's equation is dimension consistent. Okay, so let me try to break this particular question down. It's very, very simple. Very simple. We've come up with all the dimensions for all the quantities. Let's just write down the dimensions for all the quantities. I think I did all the dimensions for all the quantities. Let me just put them somewhere so that we see how we are going to prove this sweet question. I'll use another color. All right, so let's write the dimensions. What are the dimensions of pressure? What did we say the dimensions of pressure are? We said that the dimensions of pressure are simply M, L, -1, then T, like that. What are the dimensions of density? We said that the dimensions of density are the mass, then L, -3. What are the dimensions of, because we have been given this formula here, and this formula has, it has the density, it has the gravity, it has the height. What are, we know, I think by now we should know the dimensions of all these quantities. Okay, so we've written the density. What else? We have velocity. What are the dimensions of velocity? Velocity, the dimensions are, okay, no need of those brackets. Let me just wrap that. Okay, what are the dimensions of velocity? The dimensions of velocity are L over T. Because we have V to the power 2, we are going to put everything in power 2 like that. Okay, so what are the dimensions of density? We know density by now. Gravity, the dimensions are L over T power 2, and the dimensions for H is simply L, because by now we know that height, length, everything is L. Okay, now we want to prove that this is dimensionally constant. When we say dimensionally constant, we mean that what is on the right and the left are equal. Okay, what is on the right and the left are equal. So we assume that this equation is also this side. Okay, and then we know that for Bernoulli's equation, all the formulas are supposed to hold in this particular MLT concept dimension, which is simply L -1, T -2. So we must have this on our left hand side. If we don't have this, this is not going to be dimensionally consistent. Okay, so when we solve this, we must have these particular units, because these units are the ones which are on the right hand side. Okay, they hold this particular constant. Please understand that particular concept. So where there is pressure, I'm going to put my units. What are I'm going to put the dimensions. What are the dimensions for pressure? The dimensions for pressure are M, we calculated them to be ML negative to the power -1, then T -2 in the ML concept, plus constants are not added, so I won't put 1 over 2. But what are the dimensions for density? Density, we say that it is ML -3. Okay, then we are going to multiply everything by, this is going to be velocity to the power 2, so this is going to be 2 over T2, like that. Okay, I think we know where that is coming from. It's here. Then this is going to be plus density. We said it is ML -3. Then gravity, we say that it is simply L over T2. Then this is going to be H. The dimensions are like that. Then everything should be equal to M, L, -1, T, negative this. We should have this on, we have this on the right hand side. These are the dimensions for this particular equation if you've calculated everything. But we are trying to prove that this formula is dimensionally correct by solving the left hand side, making sure that we have these particular units. So let's begin to solve. Okay, so we know that for the pressure they hold, okay, so we still have m L negative 1, T negative 2, plus here we are going to solve everything. So if we try to solve that, this is going to be m over L3 multiplied by L2 over T2, plus this is going to be m over L3 multiplied by L over T2. Okay, then of course this L here and this L here can multiply to get power 2 like that. So we are going to have m L negative 1 T2 plus, then look at this and this guy can cancel. Then we are going to have m, then this L can be, in the MLT, it can be written as L negative 2. Then this is going to be T negative 2. Okay, so we have this part and this part holding. Then plus, look at this guy and this guy can cancel. We shall have M L negative 1, then T negative 1, negative 2. And everything is going to equal to, let me use, which color can I use? This one. Okay, blue. Everything is supposed to equal to m L negative 1, then T negative 2. Now, look at this. Whatever is on the right hand side is here, is also here, and the same time it is also here. Henceforth, we say that this particular formula is dimensionally consistent. Thank you so much.